Hello everyone, good afternoon. I'm Dwight Browne.
Hi, Dwight.
I will be talking about Python and Julia. And I will be answering the question you've all come here to ask. Why do we need another language? I'm pretty surprised by the proliferation of videos about this. There was someone who gave a 3-hour lecture at SciPy in July on this, and it was quite disheartening for me because a significant number of my slides literally mimicked what this guy did, where I'm saying, wait a second here, this is great actually. I mean, we're all thinking about the same things, and this guy is a professor off in New Mexico, so my slides aren't going to be anything like his, but I am going to have something that I think you'll all enjoy. Let me tell you a little bit about myself. I happen to be in the financial services space. I've been doing this for well over 20 years. Back in the early 90s, I did a lot of C and Fortran, and subsequently did some Java. In the last 5 years, I've been using Python to make my life much easier. I think the language rocks. I'm sure all of you do as well. And I've thought that I've found something that would be interesting enough to talk about, and that's the Julia language. And I'll start with a bit of history. I've watched a lot of television, so you're going to have some television references in my slides. So back in the olden days, pretty much the time period between the honeymooners and Oprah, we had computers that were relatively slow, and they required really efficient languages to get what they needed, done. You pretty much had C and Fortran. Those are the two languages that have survived over the years, and they're still around. They required really efficient and diligent coding, and as the example shows here, we're going to string copy something too big into something too small for the size of 2 big bytes, and next thing you know, you're going to have a problem. The program may work, it may run 10,000 times without a problem, it may provide some incredibly difficult errors that you're never going to be able to debug. It may create a segmentation fault, or it may bring down the machine. You don't know. It's a problem. And over time, when we ended up moving into the Seinfeld and Friends era, we ended up having incredibly compressed deliverable times, where the business was saying, no, you've got to come up and do this by next week. And if you're writing in C and Fortran, you can really start making some mistakes, and you end up having these really huge bloated applications. C# came along, Java, Perl came along, made life easier. We ended up going down to pretty much 2 environments, some derivative of Unix or Windows. You know, it's like you didn't have to worry about every other thing because those things kind of faded away. And the beauty of it is computers kept getting faster. Got a brief diversion here where essentially this is a nonlinear graph. This is a log scale y-axis here, and pretty much between, again, Seinfeld and Friends space, we had our computers literally almost doubling every 2.5, 3 years. So if you had some software that really wasn't efficient, it really didn't make a difference, because ultimately it became good enough, because all you had to do was wait till next year to buy a faster box, and you didn't have much of a problem. And it was kind of like reality TV. You know, it's It just filled a void, but it didn't really solve any problems. And so essentially, what did we have? It's like 500 channels and nothing to watch. You had these monstrously big applications with these complex dependencies, and if you ended up looking into them, all of a sudden you realize, wait a second, there's all this cut and paste code. You've got all this technical debt. And it really proved to be a problem, but it didn't seem insurmountable because we still had boxes that were running faster, and you could get away with it. And no one really seemed to notice the one big problem that was just looming over everyone while they're doing this. And that's the notorious ECLE. It is edit, compile, link, execute. You're like a hamster in a hamster wheel. You're just going over and doing this crap over and over again. You're sitting at your desk for 12 hours a day, and you've got two hours that have been wasted going through this just to deal with some minor issues. And unfortunately, we've had one other issue. More data, finite time. There's 24 hours in a day. And if you happen to have a job that has a specific amount of time that needs to run in, but all of a sudden your data is increased and you've got you have some significant inefficiencies, it's going to be really difficult to overcome that. And you can't get away with saying, oh, we'll just wait till next year, we can buy a faster box. Because the boxes aren't getting that much faster like they were back in the olden days. And ultimately, you needed a better way. The problem is that still there's the need for speed. And if you're really doing something that requires high performance, you're still stuck with writing C or Fortran. It makes no difference. And if BLAS or LPAC are in your active vocabulary, Fortran is the only answer. And if it's really fast, then you're going to be using a vendor-provided compiler because you've got to get as close to the chip as possible. But you're still hindered by the ECLA. And this is a great use case for a dynamic language in some respects. So all of a sudden, the big guns come out. We've got The Sopranos and Breaking Bad. It is, it is the hit. We've got Python. It's multi-paradigm, so if you've come from a C background, guess what? You don't need to know anything about OO, really. You can get away with writing procedural Python. You can do OO, you can do functional. You've got the REPL and Ipython, which saves a lot of time. You've got less Tim Toady for you Python, for you Perl people, where it's like, you don't have to waste all the time trying to figure out what dialect of Python, of Perl someone's written in. And the beauty of it is that now, slowness of your app will be forgiven for fast delivery. If all of a sudden it's now, guess what? I need it next week. Oh, it's done today. Oh, okay. I'm happy. And that's great for some things, but not always the case. And if you are in that space where you still need to write a performant application, you're going to have to find something that would, if there were some form of coming up with a dynamic language that could meet your performance requirements, that would be great. And then all of a sudden we have Julia. Now, where did that come from? 2 years ago, there wasn't even a formal release for the language. And interestingly enough, there have been multiple talks at various Python conferences or other conferences about the language because it seems to have a lot of promise. I'm really excited about it because the more I look into it, the more I realize this has got a lot of potential. The biggest problem is that because it is an incredibly young language, there's really, the libraries that exist for it aren't particularly mature. Because it's got excellent C interoperability, that means it's got great Python interoperability. And you can call all the Python libraries without much effort. And one thing that I really like, because I'm not that much of an OO guy, it supports multiple dispatch. So now you can focus on your methods rather than the methods of your classes. And if I have time, I'll explain a little bit more about that. Now, really, how fast is it? This is a graph from the Julia website that I colorized to highlight some stuff, and you don't really need to read it that much because I ended up distilling it a bit, because what I'm focusing on is why we're here. We're Python people mostly, but ultimately we've got Fortran showing that relative to C, it's pretty fast. It's faster than C in some situations. The green cells indicate what's faster than C, and everything else is slower than C. Ultimately, we've got something where, for the Fibonacci benchmark, yeah, it's almost 4 times faster than C. Julia shows up as being a little bit faster than C. Unfortunately, Python's coming up as 30 times slower than C. If you want to do it in JavaScript, it's 2 times faster than C, and Go is almost on par with C. But at the end of the day, we've got some significant differences in speed. Now, those numbers look really impressive. And the fact that one can get away with calling the existing Python libraries from Julia says that this has got a lot of potential. Again, I think it's the greatest thing. But ultimately, people are going to ask, what do you mean? How does this work? How is this going to work? And it's going to work because Python ends up presenting its data structures in a Py object. And you can go look at these header files to see some more examples, to see how. And within Julia itself, we have the same data structures that are implemented as well. So now you can end up passing a call off to the corresponding C library and name and get your data back without much of a problem. The other thing that I really liked about the Julia language as well, and also I mentioned there's a C call where if you want to call any external C library, it's there. It's pretty cool. Here's the Julia PyObject representation. If you notice, we've defined the type, which is essentially the equivalent of a class in Python. And you can see there is no explicit constructor for this. There is no init method. It's implicitly created for you, so once you define your type. Now all of a sudden you can just call your types. It's pretty cool. We've got our function defined here, and all the way at the bottom, within these two lower functions, you can see that we are calling the macro that will do some name expansion for us and get back the data that we are going to get from our Python libraries. And the other beauty is that we have full integration with Ipython, which again, when I saw that, I was just saying, oh my God, this is great. I gotta play with this. This is the coolest thing on the face of the earth. And here we happen to have the Ipython wire message structure, where again, it's pretty clean. When I started looking at the code, I'm thinking, wow. Initially I said, well, this is kind of, I didn't, my microphone's on the floor. Did anyone even, is the guy recording there? I hope this has been recorded, but I just discovered this. But either way, I started looking at the code, and initially I was thinking, wow, this is kind of awkward. But the more I looked, the more I realized it's pretty cool. And again, I wanted to show you this because it's very clean. So that's it. That's all, folks. I'm done. But actually, I'm not. I've got a little demonstration that I'm going to show with the integration of the Ipython notebook, and I'm hopeful that within the demonstration that I can actually answer some questions for you, and you can see whether or not you want to use it yourself. So let me get out of this. So I have the slides and the Ipython notebook posted on GitHub. So if any of you want to download it, I'll just go back to the original slide and show the URL for a moment, but I need to it's all the way down at the bottom. And if any of you look at the photograph that I have on my GitHub account, that is not a photograph of me, it's a photograph of Charlie Parker. Okay, that's good. So, I've just listed all the requirements that you're going to need to perform some of the examples I have here. And I think the two most important are that you go to the Julia website and download the Julia language, as well as a bunch of other things, and also you're going to need to have Python on your computer if you don't already have it now.
So Dwight, do they have like a package management kind of stuff?
Yes, they do. Yeah, it's pretty cool. I'll show you that as well as part of the demo. And these are some resources that are available as well, where again, there are a whole bunch of lectures explaining all of the introductory components of the language, because this is not a tutorial on Julia by any means. It's essentially a means to show what it can do and the potential it has. And like I said, we have there was a conference at SciPy where this guy gave a 3-hour lecture. There's absolutely no point in repeating that stuff since this guy already did it, and I can show other things. So firstly, biggest thing that I think you need to do is that you have to define the profile for Julia. Once you've had Julia installed and you've gone through installing all the stuff that was listed up there. Once you end up doing that, if you notice, the little SVG file shows a Julia logo indicating that, yeah, you've got the whole Julia environment running. And here, we can see where our version is, what version of Julia I'm running. This is an old version. They already have a new 0.4 version going along, already released. But the biggest thing is that as a means to just figure out what's going on with the language, it's like they're just wondering, well, what is this version info function? And here it's saying it's a generic function with 4 methods. There is another Julia function that allows you to see what methods are available for this. So if you notice, we've got 4 methods. So here I can actually see where the source code is for each method as I go along, if I just want to say, well, what exactly am I looking at? Brings me off to GitHub. I can see everything that's going on. So far, it's boring. And I'm not going to continue to go through this in its entirety, as it's going to extend beyond the 30 minutes that I have allotted. But I will come up with some things that I think are quite interesting and allow people to do what they need to do, where you can actually get away with writing what you need in Julia and then calling everything in Python that you've already written. And it will allow you to save a significant amount of time from development, as well as gain the performance benefits of this language. So I'm going to skip through some stuff now. I was asked about package management. Here in the verbose output from version info, it highlights all of the packages where in Julia land you end up getting a local dot directory with the corresponding version number to highlight all of the packages that 10 minutes, that's it? Oh man. And what's available, you can update your packages pretty easily. It's similar to the Python package management. It's pretty robust, relatively. There have been some issues that I've discovered, but I don't think they're that significant. So here we get to some of the meat and potatoes. We've got PyCall, which is essentially a large wrapper for the entire for the whole Python namespace that allows you to subsequently call your Python function. So here I'm going to just go show a quick demo that was already performed earlier. But before I do that, I'm just going to show what we have here. We've got a macro where, if you're familiar with C, you'll know what macros are and how they work. And if you're familiar with any other language like C, you're going to know what I'm talking about. If I had a PhD in comp sci and I were pursuing that area, it's like I would say Lisp was incredibly cool and I would try and come up with a Lisp discussion. But when was the last time you've seen Lisp in any production environment?
Well, the Lisp community is really excited about Julia.
Yeah.
Because it's almost a Lisp.
Yeah, and the thing is, I've read about that, and again, I don't know enough about Lisp. I just knew that when I started to delve into Lisp, again, back in the Stone Age, I ran away from it like the plague. So either way, let me speed this up a bit. So here, I'm just going to show that, where is it? Come on, let me get something. Okay, cool. So here, I have a Julia function that was created. It's going to show a Julia set of numbers. And once we get down to this, oh God, I hate how this thing scrolls sometimes. What we get down to this is now all of a sudden I can show the image from, oh, this isn't the right one, I'm sorry. Okay, here we go. This is the better one. So standard example of making a graph. So if you notice, I'm calling the local Julia instance of cosine. If you notice as well, this thing supports Unicode and you can come up with all your LaTeX characters in it. So I decided to just do that as a means of showing some functionality. I would kill anyone who worked for me who who decided to put Unicode characters in their source. But if you notice, I can call the Python plot library without a problem. The pycall macro addresses the whole matplotlib inline calls. It's automatically taken care of for you, so all of your graphs end up getting graphed within the IPython notebook as opposed to having to call the matplotlib inline call. And here, as well as I was trying to demonstrate some other things with some of the other graphing packages. This is an example calling Seaborn, where instead of having the standard matplotlib graph, I can get something that I think is a little bit nicer with just 2 additional lines. Now I'm going to move into something that I think is pretty interesting about Julia, and I think it's also the biggest selling point. So down here, and here is just some more demonstrations of basic matplotlib functions being called, showing that it works pretty seamlessly. So this is what I have here. Can everyone read this? I've got 4 functions that I've defined in Julia. I'm calling it sum. It's really not sum. I just wanted to show off the Unicode crap again. So here I've got something that looks pretty archaic in terms of its style. I've got a loop. I've got a for loop in here. I'm returning the value from the loop. Okay. I've got one that looks almost identical to it. The only difference is that here I'm addressing the implicit return value that they have within Julia, which I don't particularly like, but they think it's pretty cool. This is something that looks a little bit more Pythonic, as well as something where we just got the standard list comprehension idiom that's being implemented. And I figured, let me just see how long these things are going to take to run. So these are some of the run times that I've gotten. So for the first function, it's taken 48 milliseconds. For the second function, it's taken 800 microseconds. For the third one, it's a little bit faster. The other one, it's kind of slow as well. And if you notice as well, look at this. The number of bytes that have been allocated and the amount of time that's been spent on garbage collection versus this implementation, where it looked literally identical. Because you go back to this, the only difference that I have here, besides the implicit return, which is completely irrelevant, is the fact that I've said total was an integer here, whereas here I end up assigning it to a float val. And if we get really deep, because again, this is like a 30-minute conversation, but if we get really deep into it, where we end up showing what LLVM has done, we get to the point where, drum roll please, this is the code that LLVM ended up, before it ended up going down to the assembler layer. This is the code that LLVM produced for my initial version. This is the code that LLVM produced for the second. 5 minutes, okay. This is the code that LLVM produced for the second implementation. And what it boils down to is that Julia can be incredibly fast, but it relies on type invariance. So if you happen to have a variable, it's essentially you've got to pretty much define what type it's going to, what type of data it's going to be using, as opposed to being like writing it in Python or Perl, where pretty much, it's like your variable is this today, it's that some other time. And here, the compiler saw that we were going to have tote as an integer, but here I've got tote being divided, and I'm going to be returning potentially a floating point variable. So the compiler's got to go off and allocate a whole bunch of additional space to address the fact that it could be an int, it could be a float. It doesn't really know until it starts until it's actually running. So it's got to do this in advance, as opposed to the second example. It's saying, oh, tote's going to be a float. We've got tote getting assigned a value that's a float. We're good. We're golden. And all of a sudden, the language is going to be it's going to present incredibly fast runtime.
Why doesn't it have that problem with the 2? So like for I and 1 to n, like that could be an int. It's an int half the time, right?
Well, the thing is, it's the value at compute. The I is always going to be an int because I've defined I as an int.
Yeah.
So that's never going to be a problem.
It will be an int half the time.
It will be an int half the time, but it's not going to be an int all of the time.
Yeah, no, I'm just curious why you didn't have to do 2.0 in order to get that optimization as well. There's some type invariance in the addition too.
You're absolutely right, and that I'm really not sure about.
Okay.
But again, this is one of the things where I just wanted to be able to show how, because when I started fiddling with this, I noticed that some of the performance that I was getting was no different from what I had with Python, where I'm thinking, wow, this is supposed to be that fast, what's the issue? And the more I dug, the more I started to look, and then all of a sudden I saw, yes.
It looks like you're also declaring that n is going to be an integer. Wouldn't that have more of a performance since that's using a multiple dispatch?
Actually, no, it doesn't.
It doesn't?
No.
Like in the first one, couldn't n be anything?
It could be, but I defined n, sorry. earlier up here as an int, and I'm passing an int into the function. So that's why it makes no difference. The thing is, in the examples that they have, they don't have all of the permutations, so I figured, how could I make this how could I show as much as possible in the allotted time? So as you can see, I got a lot more stuff here going on within this, but again, I've got less than 1 minute. Does anyone have any other questions? Yeah?
Did you see on Julia website they showed Julia crushes it?
Yes. And that's what I showed in one of my earlier slides.
I'm assuming those are not like kind of NumPy using Ipython, et cetera, et cetera.
No.
How much? I mean, right there, it kind of looks like.
Remember the disclaimer. The disclaimer right here. Your mileage may vary.
Right.
So.
I was just wondering if you got a sense as to how disparate those numbers were when you're using things like everybody uses, like NumPy and stuff like that, in kind of their scientific calculation.
Not yet.
Okay.
And I've been told my time is up. So, thank you, everyone.